Hi everyone, my name is Elisa Lorenzo, and today I will be presenting on the Physics 2211 Lab 1, which is about constant velocity. So the purpose of this lab is to observe and analyze the motion of a physical object, which has to be at constant velocity and direction. We also want to compare the observed position to the predicted position, which we obtained through creating a constructed computational model, and we'll also be using the physics principle of Newton's second law. In this lab, we also used two programs, one of which was Tracker, and this was used to analyze the motion of the chosen physical object, which I chose to be an exo marker, and we used this to find the observed position. We also used GlowScript, in which we were given a model code, and through editing this, we were able to construct a computational model, which helped us find the predicted position. So the main fundamental principle that we'll be looking at in today's lab is Newton's second law. This is also known as the momentum principle, and the equation for this can be seen to the left. What this means is that the net force of an object is proportional to the rate of change in momentum of that same object. To the left, we can also see two other formulas that are derived from this main formula, the position update formula and the velocity update formula. And it's important to note that as seen by this velocity update formula, if there is no net force on the object, the momentum does not change. What this means is that if the object is already in motion, the object will be at constant velocity. First, I started out by recording and observing the motion of the exo marker, which was rolled at a constant speed and in one direction. I then used Tracker to analyze the observed motion and found the observed position. And to find the predicted position, I then used GlowScript to create a computational model. And after exporting this data, I then plotted both the observed and predicted positions on a graph, and I then compared the results. And the result of this is one position versus time graph, which is comparing the computational model to the observations. Here you can see the tracker software showing the observed motion of the object. I chose an expo marker, and this will also serve as a system. And it's also important to note that we are assuming no friction or air resistance to assume constant velocity. Now I will show a short video of the expo marker in motion. To compare our observations, I then use GlowScript to create the computational model. And you can see the edits highlighted. I had to update the velocity and positions from the model code given, and you can see that box in red. And we also had to update delta t, which was changed to 0.033 seconds due to a 30 frames per second of the recording. It is also important to note that the mass of the object will not play a role since the net force is equal to 0, so the mass will cancel out. You can see here the position versus time graph using the tracker and the computational model data. Some sources of error that may have caused some deviation include friction and air resistance, both of which would have been opposing the marker's motion and would have caused decreased velocity compared to the model. Human error could have also been a reason for this deviation, since the marker may have not been rolled at a constant speed and may have been rolled too hard in the beginning. Tracker error could also be a reason involving calibration errors or inconsistency in tracking the point of mass. And all these factors lead to the velocity not truly being constant, which would have caused a difference between our results. So what would it mean if the x-axes were flipped? In this case, the magnitude would stay the same, but their direction would differ. So instead of a positive slope, we would now have a negative slope, assuming that the positive x is now to the left and the negative x is to the right. Next question is, can we say how many net forces were added to give net force 0? Now, in this case, there are multiple forces not accounted by the model that are acting on the marker, which can be seen by the tracker's deviation from the model. And this could be due to forces like friction and air resistance. So in reality, the marker could not have actually been moving at true constant velocity due to these forces. And because there are forces in all directions, we cannot determine the exact number of external forces from the surroundings that are acting on this marker. I'd like to thank you for watching, and I hope you enjoyed.